In this chapter, we will be looking at advanced theories of covalent bonding. The problems with what we have so far is that the shape of the orbital versus bond angles do not match up, and it also doesn't explain magnetism. So the three theories that we're going to be looking at in this chapter are valence bond theory, orbital hybridization, and molecular orbital theory. We're going to begin with valence bond theory. By the end of this video, you should be able to describe the formation of covalent bonds in terms of atomic orbital overlap and define and give examples of sigma and pi bonds. VSEPR theory that we learned in the last chapter predicts the shapes that molecules will have, but it doesn't explain bonding. If we look at the shape of s orbitals and p orbitals, which we have looked at already, they only describe shape around a free atom, not when an atom is actually bonded as part of a molecule. A covalent bond forms when a pair of electrons is shared by two atoms and is simultaneously attracted by the nuclei of both atoms. Valence bond theory describes a covalent bond as the overlap of half-filled atomic orbitals that yield a pair of electrons shared between the two bonded atoms. So if we remember, in covalent bonds, usually one electron comes from one atom and the other electron comes from the other atom. So when the orbitals that hold that single unpaired electron overlap, we end up with a bond where the two atoms are sharing those two electrons. So hydrogen has one electron in the 1s orbital. Fluorine has a p orbital that has one electron in it. When those two overlap, we end up with a bond between the hydrogen and the fluorine. Same idea between two fluorines. Each fluorine has a p orbital that has one unpaired electron. When that p orbital overlaps with the p orbital of the other fluorine atom that has the one unpaired electron in it, we end up with the single bond between the two fluorine atoms. The two conditions for this to happen is there must be an overlap, a portion of both orbitals that share the same space, and the extent of the overlap determines the bond strength. If they overlap just a little bit, it'll be a weak bond. If they overlap a lot, it'll be a strong bond. And one from each orbital, one electron from each orbital, will form a pair to form that bond. And the atoms are then held together by the mutual attraction of each nucleus for the shared electrons. There are two types of overlap that we can have. The first one forms what is called a sigma bond. A sigma bond is a covalent bond in which the electron density is concentrated in the region along the internuclear axis. So we can have overlap between two s orbitals, and if I drew a line between the two nuclei, the region of highest density is right along that line between the two nuclei. I can also have overlap between an s orbital and a p orbital. Again, if I draw a line between the two nuclei, that region of higher electron density is along that line. Two p orbitals can also overlap, and we have the line between the two nuclei. That region of greatest electron density is on that internuclear axis. If I have a sigma bond, the atoms can actually rotate. So there is rotation around a sigma bond, and that'll become more important later when we're looking at how those molecules move. The other type of bond is called a pi bond, and a pi bond results from the side-by-side overlap of two p orbitals. We can't have a pi bond with an s orbital. It has to be two p orbitals. And if I look at the internuclear axis here, but combining those two nuclei, well, along that internuclear axis, there is a node, a place where there are no electrons existing. So the regions of orbital overlap lie on opposite sides of that internuclear axis, not along the internuclear axis itself. When I have a pi bond, those atoms are not, or there's no rotation around that pi bond possible. Again, that's going to play a big part when we look at how molecules actually move. So where do you find each type, the sigma bond or the pi bond? The first bond between two atoms will always be a sigma bond. So if I have a single bond between two atoms, it will be a single bond. If I have a double bond, one of those bonds will be a sigma bond. Any additional bonds must be pi bonds. So if I have a double bond, one of those bonds will be sigma, the other one will be pi. If I have a triple bond, one of those bonds will be sigma, the other two will be pi. So if I look at this molecule here and I want to determine how many sigma and how many pi bonds there are, every connection between two atoms is going to have a sigma bond. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma bonds in this molecule. The pi bonds are going to be the second bond between the two carbon atoms. So there's 1, 2 pi bonds present in this molecule. So a sigma bond forms when the region of electron density is along the internuclear axis, and the first connection between any two atoms will always be a sigma bond. A pi bond is one where there's no electron density along the internuclear axis. It's a side-by-side overlap, and those regions are on opposite sides of the internuclear axis, and any additional bonds other than a single will have to be pi bonds.